Okay, hi, this is Travis, and I'm gonna talk about this somewhat crazy idea of net zero hospitals. So I'll try to tell the story tonight, and if it all goes well, then the story should look something like this. First, I'll talk about where we're at, the current state of play in hospital energy. Then I'm going to give a critique of our national standard, that is for HVAC, or standard 170. Then I'll tell you the story of the last 8 years in building medical office buildings or clinical buildings. And spoiler alert, I'm going to announce that we've achieved a net zero medical office building at Kaiser Permanente. And then I'll come back to hospitals. I was going to do this top 5 list of things that you could start doing in your HVAC designs. But really, it's the top 2. If you want to radically improve HVAC design and energy performance, there's really 2 things to do. Okay, so let's put our systems in context. I'm going to show you about 5 pictures in about 4 minutes. This first picture is energy consumption or energy signature of U.S. commercial buildings by type. So you can see office buildings and churches and hotels, and wow, what the hell is that? That's us. That's inpatient healthcare. Ouch. I always like to point out hotels in this slide because hotels and hospitals both have sleeping rooms and they run 24/7. And a patient tower uses double the energy of a hotel or more. The next slide shows US hospital energy consumption versus other countries. North America is winning, right? Or losing, depending on how you want to look at the slide. Our North American energy signatures are at the top of the list. Canada is right there with us. But in general, we use about 1.5 times the energy of a general hospital in the UK and about triple the averages that you'd find in Germany or France. The next picture is a pie chart, which shows how we use energy in US hospitals. This one may be a little counterintuitive if you've never seen it before, because our energy use is not a function of medical equipment or the medical treatments going on in the building. It's largely ventilation. 2/3 to 3/4 of our energy use is heating and ventilation and cooling. And the single biggest use of energy that we have in US hospitals is reheat energy. So why do we have so much reheat? Well, this is why we have so much reheat. We design hospitals with a legacy HVAC method called air changes per hour. We have this table that tells us how many air changes to use for a lot of the spaces, most of the spaces in the hospital. And then this design method really sort of drives our energy use. These are the code minimums. Our design engineers tend to design above the code minimums because nobody wants to just do the code minimum. And then we tend to put these air changes into the spaces and run them 24/7. So it just sort of really drives our need for reheat. And that brings me to kind of part 2 of the presentation. I've been critical publicly of our national standard 170, which is this, the air change table. In California, this is also the basis of table 4A. And my critique is that it's an outdated paradigm. Most of the numbers in the standard are actually not credible. And it prevents us from some of the best practices that we really should be using in our designs. So before I go too negative, let me say this. There are areas in hospitals where the HVAC systems need to do some pretty clear things. We have clean spaces, some clean spaces in the hospital, and then we do have some airborne containment going on. The clean spaces that we have are operating rooms where we want clean air to mitigate the risk of surgical site infections, and protective environments for severely immune compromised patients. Basically, if you're severely immune compromised or you just had an organ transplant, then you're going to live in a clean room for a couple of weeks. And then we also have sterile areas where we're mixing pharmaceuticals, compounding pharmacies. And then we have containment in airborne isolation spaces. When someone is suspected of carrying an airborne disease, we isolate them. We put them in a room that's exhausted and held at negative pressure. If you don't know, and a lot of HVAC engineers don't know, there's a very short list of the sort of bona fide airborne transmissible diseases, and they are shown on the slide, right? There's chickenpox and measles and rubella, SARS, smallpox, tuberculosis, right? So a couple things about this slide. First off, you'll notice that there's clinical citations on each one of those bullet points. Not an ASHRAE journal article, but I mean like a medical or clinical citation that you can put on each one of those bullet points. Second is that any international standard you look at, and I've read a lot of them, the French, the Spanish, the German, whatever, they all honor these same principles. You're going to find this pretty much internationally. And then the third thing to know right here is that these spaces, the grand sum total of these spaces, make up a very small fraction of our hospitals, right? The sum of all the operating room spaces and protective environments and compounding pharmacies and all this stuff really are less than 5 or 10% of our hospital area, in terms of real estate footprint. So that's important to know. I'm going to skip this and we'll go here. In 2015, so we want to talk about all the spaces that are outside of those operating rooms and protective environments. In the other 90% of the hospital, where do we actually get those requirements from? Where do we get our air change requirements from? And that's a really good question. And I know at the local ASHRAE chapters, we contribute to ASHRAE research. Well, this is ASHRAE research. In 2015, ASHRAE sponsored a research project to determine the scientific evidence behind Standard 170. The research team looked at the 887 requirements in the national standard. They gathered up all the articles they could find. They collected 1,000 studies and articles and papers, and they graded the quality of all of the evidence. And the final pie chart is shown here. So you have 18% of the requirements that were classified as, rational inclusion, like you should submit your plans for review. There's just some rationality behind that. And then they actually found there were some requirements that were just flat out procedural. And then they found about 1% of the requirements that could be referenced back to some clinical standards. And then they found evidence for, something in the neighborhood of 7% of the requirements. They found some evidence, or they found evidence that showed that what we were doing in the standard was maybe above mandatory minimum, and then they found some where the evidence actually went against what we had in the standard and supported a change to the standard. But the big piece of the pie chart is actually over on the side there. For 73% of the requirements, there was no evidence basis, there's no rational basis, no clinical basis, really just no available evidence. This study is free for ASHRAE members, so you can read it all and see which one of the requirements fell into those. But I will tell you that the air change rates in particular, which is mostly what I'm going to talk about tonight, because they have a big impact on energy and reheat, did very poorly in this study. Almost all of the outside air and total air change rates had no evidence basis, no clinical basis, no rational basis. So the thing to realize here's the unfortunate truth if you don't know it. ASHRAE standards, including Standard 170, are consensus document. The numbers that go in the standards are not there because they met some amount of scientific or engineering validity, or even because they make sense. They're there because they win the vote. We put together a committee of national experts, and that committee votes on the standards. And at present, and really for the last 10 years, the committee for Standard 170 is very dominated by conservatism. So the vote generally goes to the idea that we should keep whatever's already in the standard. I kind of call this idea the false credibility. If a number is already in the standard, then it's certainly true because our forefathers put it in there for good reason, and therefore we should keep it. And barring some sort of sign from God that we need a different number, we'll go ahead and keep the old numbers. So then there's this. This is the California Energy Commission research project. I call it the South Bay project. It took place at our Kaiser facility in Long Beach. What's gone on here is we converted a set of constant volume high air change spaces to variable volume, and we tracked the air quality along the way. So we put sensors on the wall and tracked temperature and humidity and VOC and CO2 and particles. And we wound up with a pretty huge data set. 73 locations we put these sensors in, and we have 6 months worth of data. So there's 8 million data points. And the charts that are on this slide come from the patient rooms. You can see 2 air changes on the x-axis and then contaminants on the y-axis. A couple of amazing things pop out of this study right away. The first one is that this data very quickly debunks the idea that 12 air changes is better than 2 air changes, that just doesn't hold up in the data. You can kind of see that the levels are pretty much the same. If that surprises you, by the way, then you're not alone. It surprises me. I think we all grew up believing that 12 air changes per hour is fundamentally always going to be better than 2 air changes per hour. But think about it this way. I'm going to wear this shirt again sometime in the next 2 or 3 weeks. And before I wear the shirt again, I'm going to wash it. I can wash it one time and it'll be clean enough to wear again. Now I can turn around and put it through the laundry another 4 times or 10 times or 30 times. And when it comes out, it'll be clean enough to wear it again. It doesn't really ever really get better than clean enough to wear again. Clean enough to wear again is kind of as good as it gets. And that's the same with air quality. We don't really need a whole ton of air for hygiene ventilation. 15 CFM per person or 20 CFM per person comes out to a half an air change or maybe 1 air change. That's all you need for contaminant control and air quality. And so we often need 6 or 10 or 12 for cooling, but it's not really making things a whole bunch cleaner. The other thing that I think is amazing about this project is that we're the first people to do it. You would think that after talking about air changes for 50 years, someone would have gone in and checked whether those air changes do any good in controlling contaminants. Apparently nobody ever has. And so we did this study, and it turns out 12 air changes, not all that great. So let me wrap up on standard 170. This is a chart that I've shown in my presentations before of the standard air change rate in X-ray rooms plotted against the actor who played James Bond. I always point out that Sean Connery is smoking a cigarette, which would have been fine, in an X-ray room in 1962. But basically, you can see we've always used 6 air changes. We use 6 air changes because we've always used 6 air changes. We did have that one weird code cycle where it shifted up to 10 air changes, which roughly aligns to the single film appearance of George Lazenby as 007. But then for the rest of the time, we just use 6 air changes. And this is where I point out that most of the X-ray rooms we've built since Roger Moore took over as James Bond, most of the X-ray rooms we built in the last 30 years are in medical office buildings, B occupancy buildings. Or in California, we would call them non-OSHPD buildings. And now we call them imaging rooms, not X-ray rooms. But in the B occupancy buildings, there's no code requirement for 6 air changes. And so we tend to not use this number. We build those buildings with VAV systems and return air plenums all the time. So we have thousands of examples of X-ray rooms that we didn't use 6 air changes per hour, and there's really no reason to, right? But in our national standard, we still have that number, right? Because again, it's largely driven by the votes, and the committee is kind of conservative. We've always published the number that said 6 air changes per hour, so we might as well just keep it, right? Okay, so that leads me to the topic of medical office buildings. And I told you the story about ASHRAE 170 so that I could tell you this one. I wasn't just killing time there. Most of the buildings that we've actually built, most of the new construction that we've done in the last 8 years are actually not hospitals. They are those outpatient facilities. And so most of our new construction energy learnings have been in those facilities. So starting in 2011, 2012, we started an energy program on our medical office buildings. First things first, we require an energy model on every building. And then that energy model has to show the modeled performance of the building at an energy target. And on the West Coast, our energy target for medical office buildings was 50 EUI. Now that's the part that relates back to standard 170, because if you put 6 air changes in all your X-ray rooms and exam rooms and treatment rooms, you can't meet an energy target of 50 EUI. So when we put this program in place, we kind of officially unadopted standard 170. Wherever it's not legally mandated, we don't use the air change rates, right? And then the third component of our energy program was that we measured the results. So we would always do an energy model during design, and we would measure results after design. So this is the slide that I call our glass half full, glass half empty slide. On the one hand, I can happily report that the buildings that we opened in the time period of 2015 to 2017, compared to the buildings that we were opening prior to 2012, are a full 50% lower in energy signature. So that's pretty cool, right? I mean, our average was 140. We sort of put this energy policy in place. It took a couple of years to pick up and gain speed, but by the time we get out past 2015, our average opening was 70 EUI. The glass half empty part of this slide is that our energy target was 50. And the energy models for these buildings usually said they were going to beat 50. We had energy models that said they were going to be 45 or 40 or even 37, and our average came in at 70. So we have a lot of 40 and 50 EOI buildings that didn't actually reach 40 or 50 EOI. Well, that sucks, right? Because we need to learn from that. We need to improve our energy modeling predictions. We're routinely way off on natural gas, by the way. So we actually need to bridge that gap. There's a name for that gap now. It's called the energy performance gap. So it's a known phenomenon that between energy models and what you actually see in the building, there is a gap, and we need to work on that. Okay, but first, let me end on a high note here. I'm told that once a building is below 10 EUI, that you can essentially declare victory and take a victory lap and say that you have a net zero building. And if that's the case, then let me announce here tonight, our first confirmed net zero healthcare building is the Santa Rosa Medical Office Building, MOB number 6, we call it. The design here is an all-electric heat pump design. Our first patient was May of 2018, and through the first year of operations, the building consumed 36.8 EUI of electricity. And in the same period, the on-site solar production was 31.8 of electricity. So the net consumption, 5 EUI. We're going to go ahead and call that a net zero building. I'll admit that I have some mixed emotions about taking a victory lap with MOB 6, because I also know this building was a son of a bitch to commission. We had hot calls and cold calls throughout the first year. We withheld substantial completion for the general contractor for something like 15 months. The final commissioning report didn't get published until a long time after the building was already in operation. And there's still opening commissioning issues, I believe, to this day. But on the other hand, I've told our design teams for years that we are not going to announce a net zero building until we actually have a year's worth of data in our hands. This is the 4th design team that we've had that designed a net zero building, and it's the first one that actually achieved it with the first year's worth of data. I've seen other owners and other design teams that announce that they have a net zero building at the start of construction or the opening date of the building, and to me that's cheating. This building actually has the data to prove that it is what it says that it is, and so it's got my endorsement. I believe, by the way, that this is the first net zero medical use building in the United States that actually has the data to back up that claim. I realize that is a heavy bit of bragging, so I'm open to being told that I'm wrong about that. If anybody knows another one, please let me know. We also have another slew of medical office buildings in design and construction right now, so I'm relatively confident this won't be our last net zero medical office building. So let's get back to hospitals. How are we going to get our energy intensity of the hospitals down from 230 EUI, to a point where we can achieve net zero? And like I said, I was going to give you the top 5 list of things that you can do, but I'm actually going to come down to the top 2. And first, we're going to talk about a boiler system. Here's the big thing that I've learned in the last couple of years. Consider the fact that by about 2005, it's fair to say that most of our buildings were using digital controls, which means that every project we put out into the universe, we put in the MEP systems, and then we also put in a giant data system that creates a database of HVAC system data. And that's pretty cool, but for some reason, 90% of design engineers that I've ever dealt with don't use that data. We don't use it to validate our design assumptions, we don't use it to prove our successes, and we don't use it to find our failures. So that is my number 2 recommendation. Start using that data. And let's talk through this as an example. I've highlighted really just a very few DDC points here, right? Supply water temperature, the BTU meter, which could be a GPM meter. In this case, it's a BTU meter. Then a natural gas meter and an outside air temperature. You also would want to have a return water temperature sensor on this thing. But let's imagine at the end of construction, we're going to trend about 5 points for 5 business days at 15-minute intervals. So we're going to get a spreadsheet from the control system that has just a very few number of columns to it, right? column number 1 would be a timestamp, and then column number 2 would be the supply water temperature set point. And column number 3 would be the actual supply water temperature, and then you'd have GPM and return water temperature, and then the last column in the data set would be the natural gas volume. That's all the data that you need to validate the system design. And you'd validate the system design like this. First, you want to make sure that the supply water temperature is in control. All the points that you gather on supply water temperature should be plus or minus 2 degrees of the set point that they were intended to be. Second, I would expect that the hot water supply temperature would be working according to a setback schedule. Right? When outside air temperature is above a certain temperature, we should see higher supply water temperatures, and when it's below a certain temperature, then we should see lower supply. That should be extremely predictable, and the data that we gather should fall right in line with our expectations. Right. Third, I expect to see the capacity of the overall boiler system vary with outdoor air. This seems like a really simple concept, but trust me, when you start looking at data, nothing is simple here. But think about it, when the outside air temperature is less than 40 degrees, we should be using more natural gas in that hour than when the outside air temperature is 70 degrees or 80 degrees, right? When the outside air temperature is over 80 degrees, really we should be off or seeing very little boiler usage. Fourth, we want to see efficiency. We actually want to see and measure efficiency. Efficiency is measured by looking at the system demand, which is that GPM delta T, and then comparing it to the natural gas input. And there should never be an hour where the natural gas input is 20 or 25% higher than the system demand that we see in that hour. That would be an 80% efficient boiler, right? And then there's 2 bonus tests here. Bonus test number 1 is that if this is a medical office building or a clinical building, then from the hours to 11 p.m., from 11 p.m. to 4 a.m., we should see the system shut off, and that should show up in the natural gas numbers. And then the second bonus test is that if this system is a condensing boiler, which we very often, it's very popular to specify condensing boilers, then the hot water return temperature should always be 130 degrees or below, right, for 90% of observations. So what I've just shown here is a very simple idea, right? And that is you're going to take building system data and use it to validate the design and prove that the design is working according to the design intent. It's a simple idea, but it's also extremely radical. This is not common practice. I don't know how many people in the room have done this, but if you start doing it tomorrow, I guarantee it'll change your life. Some of you may be thinking that if we open a building in the summer, this won't work, right? You can't trend a boiler system in the middle of the summer and expect it to work out right. But I would urge you to look at the list again. These statements, these 6 statements should be true all year long. These statements should be true in an unoccupied building or an occupied building. They should be true really no matter what condition we throw at the system, all of these statements should be true. And that's one of the biggest lessons that we've learned in doing this on our buildings. It's an analogy that I like to call the 150 mile an hour car analogy. And the analogy goes, if you designed a race car to come off the block and go up to 150 miles an hour, but then you take it home and you drive it around the neighborhood at 10 to 15 miles an hour, it's probably not going to work really well. And the same thing happens with boiler systems and chiller systems. If you design the boiler system for 30 BTU per square foot, and then during the trending period, you only have 1 BTU per foot or 2 BTU per foot, well, that's tough. You may not even be able to achieve your supply or water temperature and control. Your chart will look like an earthquake, the delta T will be crap, and then you'll fail the efficiency test and you'll fail everything from that point, right? In fact, I like to say that testing a boiler in the wintertime is kind of cheating, right? Of course it's going to work when it's freezing ass cold outside. The real test of the boiler system and its responsiveness is like this afternoon when it's 55 degrees outside or 52 degrees outside, right? That's when we really should see these things working the way that we intend them to be working. So this really became a paradigm shift for us at Kaiser. This is a standard on Kaiser projects, and this is now how we do commissioning. We write numeric acceptance criteria for the building systems, and then we test against those numeric acceptance criteria during commissioning. And it turns out, what we've learned here, I guess, are that acceptance criteria fall into two categories. The first category of acceptance criteria is that you have your systems in control, right? All your rooms are plus or minus 3 degrees at the set point. All your supply air set, plus or minus 2 on your supply air temperatures and your supply water temperatures, right? The pressures should all be plus or minus a degree, a margin of error that's within expectations. That's the first, tier of acceptance criteria, is that your systems are in control. And you want to achieve that as a prerequisite, right? Make sure all your systems and all your zones and all your temperatures are in control. That's a perfectly good statement. Your building might be an energy dog, but at least you can say that all your systems are in control. The next tier of acceptance criteria comes with that energy functionality, right? The economizers are supposed to work the way they're supposed to work. The efficiencies should come true the way they're supposed to come true, right? You should see systems ramp up and ramp down according to outside air temperature, right? Those should all come right out in the data, and the data should prove that they're working the way they're supposed to be working, right? Now, I was a design engineer. I spent a whole career in design engineering prior to coming to Kaiser, and for the buildings that I designed, of course, I assumed that these things were coming true in the buildings that I worked on, because I intended them to work, and nobody ever called me back to tell me that they weren't working. So that must mean that they work, right? And of course, I'm being facetious there. What I've learned, if I've learned anything in the last couple of years, is that when you get into these acceptance criteria and the data validation of the system designs, it's a huge sort of mental shift. It can be very humbling or deeply humiliating, because when you're wrong about something, about one of your design assumptions, the data won't lie to you or sugarcoat things. The data just tells you the way that it is. And it's huge. It's a tremendous learning opportunity. I think I've learned more about system design in the last year and a half since we started doing data validation of the systems than I learned in a whole career before that. So that's my number 2 recommendation. Use system data to validate your system design intent. Make sure that it's working not just at 150 miles an hour, but also at 5 miles an hour or 10 miles an hour. Okay, so this will bring me to my last recommendation. All right, number 1 recommendation. Last winter, we went to Europe with ASHRAE, and we toured a hospital in the Netherlands. And while we were there, the building engineer walked us around the building. It was after hours one evening, about 7 o'clock. And so we did the tour, and as we walked into the admin spaces in the D&T block in the conference center, he kept apologizing. He said, "Oh, I'm sorry, it's already getting cold in here, but we shut down all the systems at 6 o'clock." And we're like, "Oh, that's no problem, that's no problem." And it didn't really register with me at the moment, but back at my desk a few months later, I was reviewing this job that's on the screen here. And the engineer was proposing a constant volume, 24/7 system. And I looked at the room schedule, and I don't know if you can see the room names, but I saw that about 75% of the system was administrative areas and D&T. And that's kind of when it hit me. I said, wow, we're going to spend $2 million on an air handling system and a set of controls in 2019, and we're going to put in a constant volume reheat system to serve a bunch of these admin spaces. Now, if we were electrical engineers, we'd be shot for proposing a lighting design where all the lights run 24/7. But in hospital HVAC, we do this all the time, man. And remember that the biggest use of energy that we have in hospitals is reheat. And in ASHRAE, we know how to get rid of reheat. It's called VAV. And in every other building type outside of hospitals, it's required by Title 24 and ASHRAE 90.1, and we've been doing it for years. Off hours, you reduce the air. Even during hours, you reduce the air down to the code minimum before you turn on the heat. So you got to reduce to code minimum, right? All right, let me show you some data. I like data. This is a picture for you, and this is real data. This comes from one of our hospitals in Portland. This is a hospital tower, 340,000 square feet, and the data that I'm showing goes from September to November. So you can see outside air temperatures ranging from about 90 degrees, outside air temperatures, the green line, down to about 40 degrees. Design capacity for this system is 350,000 CFM, which is about a CFM per square foot, or somewhere in the neighborhood of 7 air changes per hour for the whole volume of the building. That's the design peak capacity. And on that note, it's a good thing that we have VAV here because even on the 90-degree days, we don't need that. We don't need full capacity. We only really use 80% of that, right? We're running at 0.8 CFM per square foot or 5 air changes, for the volume of the building. That's pretty good. But the lowest number on this graph, barring a couple of those outlier points, is this 240,000 CFM. That's 0.7 CFM a square foot, or it's almost 5 air changes for the whole volume of the building. That's the lowest point on the graph. And the reason I'm showing you this building is because I actually think this is pretty good. I spent about the last 6 months looking at operations, talking to design engineers. I think there are hospital designs in the country that do better than this, that have more turn down than this. But frankly, I think this is pretty good. I think industry-wide, this would be considered pretty good VAV. I think this is crappy VAV. Let's be very clear about that. And so let's talk about the design need. Okay, so we're going to play a game here. For the last year, I've been collecting data from our designs. We've done about 1 million square foot of air handler projects in 2019. And every time we do a project, I log the room names and the square footage and the design CFMs into this giant spreadsheet. So I've made myself this database, right? And what you see on the screen here are the top 30 spaces in hospitals by frequency, and I've grayed out the top 10, right? So, and hopefully you can't see behind the gray. So go ahead and shout out some answers. What do you think are the top most common spaces in hospitals, right? Okay, so there they are. First off, remember in the beginning that I mentioned that isolation rooms and operating rooms and protective environments and compounding pharmacies are less than 5% of a hospital's footprint. And you can see that. You can totally see that in the data, right? Operating rooms are way down on the list. Isolation rooms way down on the list. They're actually less than 2% of the footprint of hospitals. So the number 10 through 1 spaces, I'll point out a few of those. ICU patient rooms, number 10, those actually have a different code requirement than normal patient rooms. But on average, our design engineers are designing those for 9 air changes. The code minimum is 6 air changes, which means you can easily do a 30% turn down. Exam rooms, I think I've already sort of talked about based on the outpatient stuff. The 6 air changes that's in the code is kind of silly, but our designs are coming in at 8 air changes. And so you can turn those down to 6 air changes during operating hours, and you can turn it down when they're unoccupied. Worst case is California, where you can turn it down to 25% when it's unoccupied. So your overnight minimum there will be 2 air changes, right? Conference rooms, we're seeing our design engineers design these for 8 air changes. That's an opportunity. That's a 90% turn down opportunity, right? Those could be almost completely shut off if you had an occupancy there. Look at the top 3 though. Look at patient rooms. Our average design engineer puts in a peak of 9 air changes in the patient room. For the minimum, California has the advantage. Anytime you're in economizer mode, you can drop to 2 air changes, which is an 80% turn down. But even outside of California, the minimum is 4 air changes, which is a 60%. The second most common space in hospitals is administrative areas. It is almost 20% of the building footprints. And our design engineers have been putting in 8 or 9 air changes of supply air on average. Dude, you can turn that down 90%. Worst case code minimum overnight is California. You could drop down to 25% of 4 air changes, which is 1 air change. The overnight minimum is very, very low in those spaces. And the single most common space in hospitals is corridors. We have miles and miles and miles of corridors. A quarter mile of corridor for every 100,000 square foot of hospital. And our design engineers tend to design those at an average of 5 air changes per hour. Everybody looks at that and says, wow, that's crazy. I don't know why they're doing that. But then everybody submits their plans and the numbers don't lie, man. The code minimum there is 2 air changes per hour. That's a 60% turn down opportunity. So you're hearing me say these numbers, 60% turn down opportunity, 90% turn down opportunity, 80% turn down opportunity, right? Where the chart that I showed you before, we're only turning down 4%, right? Let's get back to this chart, all right? So my database has also allowed me to do some code analysis. What would the average code minimum actually be at different times of day? So let's start off. In an average hospital building, this is a full-blown hospital patient tower, by the way. But an average hospital building, you should see a code minimum that's about 0.55 CFM per square foot, or just under 4 air changes for the whole volume of the building, right? In California, that's a little bit lower because of the patient room thing, but only by a marginal, a percent or two. That's the daytime code minimum. The overnight code minimum drops down significantly. Some of these spaces can shut off, others can turn way the heck down, but the overall code minimum at night should be about 0.4 CFM per square foot, which is more like 2.5 air changes for the volume of the building. That's still quite a bit of air, by the way. 2.5 air changes for the volume of the building is still quite a bit of air. The ventilation minimum, by the way, generally driven by the exhaust, and that comes in at about 1.5 air changes for the volume of the building, or 0.23 to 0.25 CFM per square foot. The outside air calculations drop off the bottom. You only need about 0.15, 0.2 CFM per square foot of outside air, and so generally it's less than an air change. So it's always going to be the exhaust, or at least in the scenarios that I've looked at, it's generally going to be the exhaust that drives your ventilation. Okay, so this is more of the range that we should be seeing in the VAV systems, right? Let's zoom in a little bit and show you what I think VAV should actually look like, right? Obviously, when it's really warm out, when it is 90 degrees, then we should be seeing, we should be going up to the peak. But in the mild temperatures during the day, we should be dropping down to that occupied code minimum. On the overnight basis, we should be dropping down to that unoccupied code minimum. And we should be seeing this pretty routinely. And we can be very numeric about this when we do projects. Here's a set of acceptance criteria. First off, all the zones in the building need to be plus or minus 3 degrees of their set point. That's our acceptance criteria for zones. Second, we should see supply air temperatures plus or minus 2 degrees of whatever the set point is. We do expect our systems to have supply air resets. So when the weather is cooler, we should have outside supply air temperatures at 60 degrees, and then when the weather's warmer, then your supply air temperature should drop down. Relative humidity, if there's a room that has a code required relative humidity range, put a relative humidity sensor in that room, and you should be within the range for 80% of observations. We can argue about that because that's a much broader criteria, by the way, than plus or minus 3. But that's the way that we track it. Obviously, any room that has a pressure requirement, you should put a pressure sensor in that room, and it should be within pressure range for 90% of observations. Actually, I should say any critical room with a pressure requirement, operating rooms and isolation rooms. You don't need to put pressure sensors in the clean linen storage, boys. Right? Economizers need to work. They should be 100% open at the right outside air conditions. Your CFM should be at 90% only when your outside air temperature is over 80 degrees. So if it's not 80 degrees outside and you're seeing your systems ramp up to the top, then something is wrong. You shouldn't accept the system. During the day, we should see our airs drop down to that code minimum when the outside air temperature is reasonable. And of course, between 11 a.m. to 4 a.m., 11 p.m. to 4 a.m. when the outside air temperatures are reasonable, we should see our systems drop all the way down to that unoccupied code minimum. So by the way, I just made 9 statements there, and all 9 of those statements should be true all year long, and all 9 of those statements can be validated by building system data at the time that you commission the building. All 9 of those statements should be true whether the building is unoccupied or occupied. All 9 of those statements should continue to be true throughout the life of the building, right? If you're a design engineer, by the way, I'll send you a Word document that has those 9 statements plus about 4 to 10 more that are provable. And if you're a design engineer, I would say put those criteria on your plans and measure them as you go out or as you close out the project. So I know when the guy from Kaiser comes in to talk about net zero, you expect to hear all about these topics that are listed along the bottom here, right? Heat recovery and energy exchange and decarbonization, microgrids, renewable thermal, all that stuff. Those are all very exciting topics, and they are going to be part of our journey to net zero. But instead, what I talked about some seemingly unsexy or unexciting topics, boiler commissioning, VAV design. And I totally did that on purpose. I've never had any problem finding somebody who wants to talk about heat recovery or thermal storage or microgrids, because those conversations are fun. The stuff that we need to do is the unfun stuff. It's very basic. We need to be brilliant at the basics. We need to reduce our demand and then work on efficiency from that point, right? So I'll tell you one more story just to kind of close this out. I showed you data earlier from that research project that we did in Long Beach, where we collected the air quality data at the different air change rates. Well, we had a nice big failure in the middle of that project. You always learn from failures. Failures are the best, right? Me and the design engineer were on the phone, and I remember talking to him. We said, hey, we'll program all the patient rooms to let them go down to 2 air changes per hour, but they probably won't all go there at once. You know, we'll have some diversity. Some will go to 6 air changes, some will drop to 4 air changes, that kind of thing. And we were totally wrong. Once we uploaded that 2 air change minimum, all the spaces dropped straight down to that minimum, and they stayed there. And I mean, they stayed there. The air dropped down so low that we failed the system for having too little air. It cost us a month troubleshooting that system to get it back up online. And here's what I learned. Think about this. Imagine you're in Long Beach, California, just under Los Angeles, and it's the first week of April. From 11 p.m. to 4 o'clock in the morning, the outdoor air temperature is 70.0 degrees. There's no solar load. There's no heating load. There's no outdoor cooling load. Any light in the building that can be off is off. The patients are asleep. All their lights are off. All the medical equipment in the building is either off or it's on standby. The parking lot is 80% empty. The staffing is down to 1 staff per 1,000 square feet or 1,500 square feet. There's no load in that building. I mean, on paper, you could show that there's maybe 5 BTU per square foot or something like that. But when you actually look at the system data, the outside air temperature is 70 degrees, the room temperature is 70 degrees, and the supply air temperatures are 70 degrees. And I mean, like everywhere, there's just no load. And my theory is that that's not uncommon at all. In hospitals, we have a lot of hours per year where our spaces are pretty quiet and we're burning energy during those times. If you want to design an energy efficient hospital, design it for 3 o'clock in the morning in the spring or 3 o'clock in the morning in the fall when it's 70 degrees outside and there's no solar load. And then commission it for that time period. Make sure that all your systems are turning down the way that they should turn down, and make sure that you're dropping your demands the way that you should be dropping your demands. And then use heat recovery chillers and thermal storage and microgrids and get to net zero. Okay,